Welcome to our talk titled Bromination of Fluorescein, a Facile Model Experiment for Electrosynthesis and Chemistry classes. In the next few minutes, we will present several experiments that focus on electrosynthesis as a chemical process and highlight the didactical possibilities of these experiments. Before that, we will briefly look at the concept of electrosynthesis itself and its connection with the principles of green chemistry. But first, we would like to introduce ourselves. I am Philipp Landfermann. I studied education in chemistry and biology at the University of Göttingen, and as of 2021, I am a PhD student in chemistry education.
I am Christoph Weidmann and I studied chemistry at the University of Gießen. After research on nanoporous materials and anodes for lithium-ion batteries, I'm now working at the Department of Chemistry Education of the University of Göttingen on the development of school experiments and science outreach activities. First of all, we'd like to give a very brief introduction to organic electrosynthesis. With this synthesis method, the formation of product compounds can be driven by electric energy. This can play a valuable role in future processes to make chemical production more sustainable and efficient if the used energy comes from renewable sources. In general, an electrosynthesis can be carried out as a direct oxidation or reduction on the electrode surface as shown in Figure 1. It's common to pair the anodic and cathodic process to synthesize two valuable compounds, which is not shown here. In the next example, an electrosynthetic pathway is shown where an intermediate is formed electrochemically, which reacts then in situ with the actual substrate of the reaction. In this case, intermediate cationic sulfur species can react with aromatic substrate to form an organic sulfide. In most cases, electrosynthetic processes can fulfill some of the 12 prerequisites for green chemistry. This includes the use of renewable feedstock, efficient use of energy, benign solvents, and thereby an inherently benign chemistry for accident prevention. In this contribution, we present the electrosynthetic bromination of fluorescein to eosin Y via the in situ formation of intermediate bromine. This elemental bromine is the active bromination species and will react immediately with fluorescein and showing low concentration of bromine to reduce hazard risks according to the green chemistry concept, what's also important for use in chemistry classes. The bromination of yellow fluorescein thereby yields red tetrabromofluorescein, also known as eosin Y or acid red 87. Compared to other electrosynthetic reactions, the presented system has important advantages, why we propose this as a model experiment for schools and experimental laboratories. Since fluorescein and eosin Y can be easily distinguished by their color, the reaction is easy to observe by the naked eye. The experiment is inherently safe due to the low voltage of around 3 volt and very low bromine concentration. Furthermore, this experiment does not involve complex setups like flow reactor and can be carried out in beakers and with cheap graphite and iron electrodes. The intense color allows very low concentration of substrate and product to be detected, which corresponds to low amounts to be converted. This ensures that the reaction can be completed in a very short time, making the experiment visually appealing and easy to implement in a lesson. We are convinced that this model experiment is very well suited to show that electrosynthetic processes can play an important role for organic synthesis.
The synthesis of eosin Y is done in a simple way with methods which are already known in chemistry class. A solution of potassium bromide, sodium hydrogen carbonate and a small amount of fluorescein is electrolyzed to generate eosin Y using graphite and iron electrodes. In Figure 3, the solution can be seen at different electrolysis times. On the left, the non-electrolyzed solution is shown for comparison, and on the right, the solution can be seen at 30 seconds, 1 minute, and 2 minutes of electrolysis. The longer the electrolysis is carried out, the more eosin Y is produced. This is shown in the change of color from yellow to red depending on the time. Not shown here is the intense green fluorescence of the fluorescein under UV light, which decreases over the course of the electrolysis. The solutions obtained can be studied in more detail in the next step. To show the effect of the different reaction times semi-quantitatively, a thin layer chromatography is performed. The mobile phase used consists of a mixture of methyl-ethyl ketone, ethanol, and ammonia solution. The results of this TLC are shown in Figure 5 under both daylight and UV light. Sample 1 represents the reference solution with added commercial eosin Y samples 2 to 4 the respective different electrolysis times of 30 seconds, 1 minute and 2 minutes. Sample 2 and 3 show 3 more spots in addition to the expected spots of unreacted fluorescein and newly produced eosin Y. These spots can be assigned to the 3 possible incompletely brominated intermediates. For this, I would like to draw your attention to figure 4. Eosin Y is a quadruple brominated fluorescein. The also formed mono, B, and triple brominated intermediates are responsible for the additional spots. Sample 4 shows a complete bromination of the fluorescein, therefore only 1 spot is visible. This shows that after only 2 minutes, all of the fluorescein has been converted to eosin Y. The experiments shown so far demonstrated synthesis with very low fluorescein concentrations, making product recovery impossible. However, the color gradient during the reaction is clearly visible, and the experiment can be carried out very quickly. The performed TLC showed visually nice results, but the spots are partially very close to each other. An alternative synthesis involves greatly increasing the fluorescein concentration to allow product isolation. This allows additional laboratory skills to be practiced and also opens up further theoretical learning opportunities. As an added bonus, the TLC spots are more clearly separated using the recovered product. However, tracking the reaction process is more difficult since the color gradient is no longer clearly visible due to the high concentration of fluorescein. Both syntheses have their benefits and disadvantages, therefore a selection should be made according to the desired learning objectives. As already mentioned, a later product isolation requires a significantly higher concentration of fluorescein. The remaining parameters of the experiment remain the same. Due to the higher concentration, however, electrolysis must now be carried out for at least 5 minutes. The product is precipitated by acidifying the solution with hydrochloric acid. This leads to the protonation of the carboxylic acid group and the phenolic hydroxyl group. This decreases the polarity of the molecule, lowering its solubility in water, leading to precipitation. As in the previous synthesis, a TLC can also be performed here. For this purpose, the solid must first be dissolved in an aqueous solution of sodium hydrogen carbonate. The number of spots corresponds to those of the previous experiment. This time, however, the separation of the spots is more clearly visible. The spots are assigned to the respective bromination levels in figure 8, where A represents unreacted educt, E represents the fully brominated product, and B to D represent intermediates discussed earlier. Due to the high fluorescent concentration, full bromination cannot be achieved even after 5 minutes of electrolysis. Interestingly enough, even the commercial eosin Y contains incompletely brominated impurities. To prove the generation of elemental bromine, which acts as an in situ reactant, the synthesis is performed without fluorescein. An electrolysis of 2 minutes shows a clearly visible yellow discoloration, as you can see in figure 9 on the left. This indicates the presence of bromine. The addition of an alkene, in this case cyclohexene, leads to decolorization of the solution due to the addition of bromine to the double bonds. This again can be seen in figure 9. Now that we have looked at the different experiments, what are the didactic possibilities and considerations? First of all, from a practical point of view, the experiments are facile and inexpensive to perform. The synthesis can be executed with common electrodes and comparatively low voltages in a simple beaker. Also, the TLC and filtration does not require any extraordinary equipment which should not already be available in the school. From a didactic point of view, the experiments offer multiple opportunities for theoretical and practical skills. The isolation of solid product by precipitation is a common and essential laboratory method. The same applies to TLC, and the theoretical basis of the influence of polarity on TLC can also be explained here. Furthermore, structure-property relationships can be illuminated in the TLC and precipitation of the product. The selection of the experiments should therefore be made according to need and available time. Finally, the possibility should be mentioned to let the students engage in an exploratory approach to prove part of the reaction mechanism via the bromine verification using a detection method they are already familiar with. Thank you for your kind attention and stay safe.